Our humanity is not bound to any set of restrictions, but the technology we build to propel us further. Space as a resource is almost incalculably large and pretty overwhelming to take on alone. Yet, as a group, we developed a suit which places value on the most important factor in space exploration, which is the health and safety of the astronauts. No one wants to be a lab rat, and we are far away from having to put ourselves at great risk for the reward of advancement. Down on Earth, people view the world as quite enormous, but up in space, it's an expansive new horizon beyond comparison for us to pursue. An invention such as a simple monitoring suit gives people the confidence to look above the clouds in the sky and feel comfort in what some see as a void of space. Together, we can feel even closer, knowing that each other is in good health, and despite some storms, we can see a spring.
The HEV suit is a vest that can be adjusted around the person to fit snugly and does not hinder the user's movement. The vest can be picked out specifically for its easy containment and the protection of the hardware we needed. A question that would stem from such an optimistic ground is, how does it create a healthy environment for the wearer? And why is it important? The simple answer is by giving the user a base for feedback on their own health. We all worry for our good being and even look up symptoms when we might feel a certain way. The feelings of having help behind you despite not being there is a good fertilizer for hope, determination, and having the subject of your well-being shared and monitored by others will allow your mind to relax and stay optimistic despite taking flight on your own.
A eureka moment we had when building this health evaluation vest. The brown board does have quite a liability, as everything is compact into one board, yet with a safety cache put right on top of it, somewhat like a little shell for the vest, we have something to make sure that all this hardware is protected and safe. And here we can see the Max 3102, then we got the temperature sensor, and on here we got the accelerometer. Something that did come at a cost was, in total, this was 24 solders, so that was a bit of resource and time dedication placed onto getting this onto the board. Yet the dedication was completely optimal and allowed us to have a better experience. It's actually 3 sensors: the MPU 6050, the DS18B20, and the Max 3102. Now, the first sensor is the MPU 6050. The MPU 6050 being an accelerometer which allow us to get coordinate points on X, Y, and Z based off the 0 point on when the HEV suit were to activate. And the second sensor is the DS18B20. The DS18B20 being a simple sensor that we put right above the abdominal near the armpit, and that is a temperature sensor. This allows us to get temperature recordings on the core body temperature. The last sensor is a Max 3102, which we lengthened up to the ear as it is the most applicable and standardized placement for a heartbeat sensor, and it gives us stable recordings at all times. Perfboard, a small brown perfboard with a grid of many capabilities. It goes from Y through X, and it goes from 1 to 25. Now, the amount of solders that we used in total were 25 solders. That includes the series that we connected all together to save efficiency on how they were to be corresponding to each other, and a very complicated matrix up here, which was a 4x2. And each one had to be connected 2x2 and not connected to each one side by side. Now, we chose the perfboard since it was efficient in continuing all 3 sensors in a compact, suitable space. And it was efficient since we could have everything compacted right in this pouch right here for our HEV. Now, one would say, why don't we just use the ESP32 rover? And it was a design choice that we decided to approach because the breadboard itself is large and cumbersome and does not completely fit there. We can't close it, so obviously that creates a scenario where we have to saw this off, and that just creates even further complications of not working at all. All the sensors are fitted perfectly to their 3-volt and to their ground and the GPIO pins that are needed to function with the code. We have the heart rate sensor up here, which has a curved alligator grip, which goes above the earlobe securely and pressures into the center instead of the earlobe, which allows us to have a secure pressure for the heart rate sensor Yeah, not too much to cut circulation. Then we have the DS18B20, sits above the pectoral or somewhere near the armpit, which it isn't closed in space and creates a heat. And finally, the easiest one was the accelerometer, which was the MPU 6050. Sit right onto the perf board right here, and it allows us to have a constant spacing, which is center mass, and allows us to secure where the spaceman or whoever is wearing this, the user, would be at any relative space, time, acceleration, or point on the XYZ.
This program allows the user to view and monitor data collected from each of our 3 sensors. To transmit our data, we've created a web page using HTML and CSS, which includes the collected data from all 3 separate sensors to be sorted and displayed on a local network. To write and transfer the code, we used Arduino IDE for the ESP32 microcontroller. We modified the original code to use soft AP, which utilizes ESP32 as an access point to broadcast the website. A local network allows us to access and view data without using a connected Wi-Fi server. We chose a local network as it would be consistently accessible despite differences of geographical location and widely more available to access in space.
For our design, we had to decide each place that the 3 sensors would go. The variables in which we considered were accuracy, comfortability, and stability. For example, we had the decision on where to place the MAX 3010-2 sensor. We considered many different spots, such as the arm, finger, and ear. We found that the ear was the most accurate of data readings that we received. For the DSB118B20, we discovered that the best place for the sensor was the underarm because it provided the most accurate data and most comfortability. Finally, we situated the MPU 6050 in the middle of the vest as it would provide the most accurate readings of movement and orientation.
We would like to acknowledge San Diego Miramar College and Professor Gino Bochicchio for hosting and supplying tools and facilities. We would also like to thank NASA and the California Space Grant Consortium for providing the resources for this tremendous opportunity.